got this. Yeah. So again, this class will be all about asymptotes. Yeah, asymptotes. Okay. So we all know that asymptotes are very, roughly speaking, very important. But the key features of this class, let me just mention. Okay. So we will try to define. Okay, we'll try to describe. Not just describe and interpret. Maybe interpret and describe are the two things which you want to do. Describe and interpret, because defining them actually can become tricky. Well, not tricky, but yeah, no, but we won't try to define it in very regularity. This is number one. And yeah, and then maybe techniques to calculate. Okay, calculate, especially the slant asymptotes. Okay, calculate. These are officially called oblique asymptotes. Yeah, asymptotes. Maybe these two things. And then I also want to go into asymptotes of not just graphs of functions. Okay, functions are one type of geometric object which you see in the plane, right? But I could draw any sort of geometric curve and it may not be the graph of a function. Okay, but general sets we will not do, because there is maybe, I don't know if there is anything much interesting there, but we will try to do for parameterized curves. These are just the next thing to functions, because these are like functions, right? But output is two variables. The parameterized curves, like, circle, t going to cos t comma sin t, but that's a closed curve, so that doesn't have asymptote. Then maybe we can look at a little bit details of asymptotes of rational functions, polynomial by polynomial. Okay. And lastly, which is the most interesting thing, is we want to, so from functions, we generalize it to parameterized curves. Okay. Because graph of a function is also like a parameterized curve, right? So if you have y equal to fx, then it can also be seen as a parameterized curve. You can just say that x is going to x comma fx. Not very insightful, but it is, right? It is, yeah. But then we want to go generalize these two things and go to algebraic curves. Okay. But algebraic curves is not something new. It's like conic section, hyperbola. Basically, x and y are like, you guys know this as not algebraic curves, but implicit equations. This certainly right? Just implicit equation. The word implicit is, making it explicit what it means. So implicit equations. Just let's call it implicit equations, right? For these, what can we say? Okay. And here what, and I'm just telling you these things because even if I can't complete it, you see, most of this what I'm going today, I've intentionally just kept it in an organized way. Well, not intentionally, because my knowledge is also pretty limited in this. At least what I can say in a class like this is pretty limited, and in general it's limited for this topic. So implicit equations, so I was going to say that all of this you can find, but don't Google it now in the class, otherwise you may, you'll miss the fun maybe. But yeah, most of it will be there in Wikipedia, but definitely there'll be much more details, which I will not go into, which keep it in the syllabus kind of thing. Implicit equations, and here I will try to describe a very interesting way. Okay, we will try to put asymptotes and intersections, okay, on an equal footing. Okay, so we will try to build a type of model. Okay, we'll try to extend our plane in a certain way that being asymptote can be talked about in the same way as we talk about intersections. Like, you see, two lines are parallel, but in more mature places, you will see that two lines meet at infinity. So you see what that does is it captures the parallelness, which seems like an exception, but it captures it under the same language of intersection once you introduce a new point called infinity. Right? This is a silly, which all of us know, but we will try to do this for general these kind of things, asymptotes where a new kind of space we can build. It's very simple. It's just be very simple. And then it will have a very quick computational application, and which I could just tell you directly, but to see that picture can be useful in many ways. At least I've seen in many places. Okay. So this is the plan. Okay. So that, yeah, you guys can, yeah, work it out, because we don't have, much time to do many classes on this. So we'll probably only do one class on this. So let's go a little quick. So we'll go a little quick also. So I mean, so as usual, maybe I should ask, okay, so I have, so this is in my mind, so no need to, yeah. So now let me ask you, if I put this thing asymptote, because it's very important for you to have a model of it on your own, to think about it, yeah, so that when formulas fail, you can work out things, yeah. Asymptotes to a function. When you see this phrase, then what do you think? What does it mean to you? Asymptotes to a function. Just like a quiz, MCQ type thing, question. Just one word, 2 words, phrase. What does it mean to you? Okay, so that's okay. That's fine. Yeah, Rasa bro, you had a definition. Same. Okay. Chandan, you have anything about what do you mean by asymptote to a function? So you have said two interesting things, right? So others have also said, but the key thing here, one key thing which Chandan has said is line. Yeah, we want our asymptotes to be lines. Okay. Now tomorrow in the CMI entrance, they may define, a paraboloid asymptote. Yeah. Then your asymptote can be a parabola also. I mean, they will give some easy question, not some theory, but you see, asymptote here, we are dealing with linear asymptotes. Okay. So linear asymptote. So, okay, we are dealing with linear asymptotes, and our goal here is to understand the function at infinity by using a line. This, so this could, okay, approximating a function at infinity using a line. Just like we approximate functions at a point by using a tangent, and the slope comes from derivative and so on. This is the same thing. This is the same thing, but only that the point is not an ordinary point, but it is at infinity. Okay, but here the key fact is that it has to be a line, and this is important for calculations. You will see this quickly gives the answers. And second is it approximates the function, right? So this is L, and maybe let me just say fx minus L goes to 0. So what should I put here in limit? Should I put a limit or anything? Anyone? Yeah, I should put a limit, right? I should put a limit. Now, what should I put x tends to? Certainly. So x tends to infinity is certainly there, but is it going to capture everything? Is it going, are there any kinds of asymptotes you can think that you may miss if you do this? Anyone? Yeah. Are we going to miss any asymptotes potentially? I mean, obviously, we may not miss in most cases, but can we miss any asymptotes if we do this? So no one has an answer. So now the question is, oh, limit x tends to infinity. Yeah, that's all. Limit x tends to infinity, fx minus L goes to infinity. Oh, okay, no problem. So for everybody else, is it? Please, someone confirm. Yeah, Chandan, can you say? Okay, no problem. Okay, is my voice not clear? Yeah, yes. Okay, sir. So do you see everything on the board? Like, do you see that limit x tends to infinity, fx minus L goes to 0 is written? I'll say the question, but is that okay? That's good. Okay, that's fine. Oh, so my question just is that, are we missing anything? If we take x tends to infinity, are we missing any types of asymptotes? Any type? X equal to 0, yeah, vertical asymptotes you'll be missing. So that's number one. And also Raghav has said an interesting thing, x tending to minus infinity. I suppose we also need to take that, right? So yeah, so let me not then write this at all. Yeah. Okay. So the point here is that x, so I mean, the point is that asymptotes can happen anywhere. Okay, I mean, asymptote doesn't mean that it has to happen at infinity. Okay, in the sense that, I mean, at least one of the values that's turned to infinity. I mean, so the graph and the curve, sorry, the graph and the line, they get closer and closer to each other, and the distance from the origin increases. But that doesn't mean that x and y have to both go to infinity. Yeah, so either x can go to infinity or y can go to infinity. Yeah, or x can go to any point. That can also be possible. Yeah, or infinity, or let me write minus infinity. You have to check all these things. Obviously, yes, exactly. That's what I'm saying. Yeah. So in general, you have to check all. So if there is any point A, and that point is, like I said, usually at infinity, like if it's an oblique, yeah, if it's an oblique if it's an oblique asymptote, then you can capture it, because if it's oblique, then that closeness will happen at infinity. I mean, when x goes to infinity, right? Because x has to go to infinity or minus infinity. So you're safe. You will get that with infinity. But vertical asymptotes, you have to check at A, right? So just like, yeah, Raghav said, you can take a tan x, or this is not the graph, but yeah, you know the graph like this. Okay. But usually you will know what to do, which to take. That's right. So basically, you have to check the points at which the function, um, you know, becomes more and more like a line. Yeah. But the next thing that I want to mention, which some of you have said wrong, and this can be a problem, this can lead to problems, is that asymptote doesn't need to, like, should not touch, but asymptote can touch the graph. It can cross the graph. It can cross the graph infinitely many times. Okay, so asymptote can. Yeah, so I mean, that is clear, right? Just like a tangent can cut the graph at other points. Why not? Yeah. So asymptote can cut the graph. It will obviously go and become tangent, but it can cut also, like this. So that can also happen. Okay. Yeah, so no problems. Adish has joined late. So we have just taken the definition of asymptote. That's all. And let me just start with the problem now. Okay, let me just go over the problem. So we have not done any theory so far, but yeah, let's go to a problem. So then this we can all try it out. Okay, so this is problem 1. Okay, so yeah, I think it's better to be get started with. So I'll directly start with an example which is not that of a function. Okay, it's that of a parameterized curve. So, oh, now it's okay. So let me just turn off the video. I think, yeah, that's creating a problem. So unnecessary problem. Okay, now it should be, let's see, you tell me. Okay, so it's problem number 1, and this is about finding asymptotes, finding asymptote of a parameterized curve. Okay, so what is it that I'm saying? So you look at this thing. So x equal to t plus. So you will see that this is a example I've taken, and then y equals to t plus cos nt comma nt by t. Okay, so this is a parameterized curve in the sense that when yeah, the values of t change, so you can just say that t is in r, and as the values of t change, this becomes a function from r to r2, right? So you'll end up plotting something, right? So as you change the values on the real line, yeah, as you change the values on the real line, you will end up plotting something. I don't know what that will be. Okay, I mean, it's definitely not something like this, but let me not try to plot it because that will maybe give the answer. Okay, so find the asymptotes. Now note that we have not even defined what asymptote means for this thing, but we all have a rough idea. So let's just try to find it, and then we can have better idea if needed. Yes, yes. Oh, no, no, because yeah, many two people have not yet written. So yeah. Okay, so you're saying the line y equal to y so you're saying y minus x equal to 0. Okay, so the set of points. Okay, okay, okay. Okay, so you have said the answer into the rough explanation. Okay, let's see what others can say about this. Yeah, so don't try to don't try to, get an equation, don't try to eliminate the parameter. Okay, it's possible as you can see, but um, it's much simpler than that. So already we have an answer. So I'm just seeing if others. Hmm. I mean, so we can just do it like algebraically, right? So you can assume like if you can say that if y equal to mx plus c is an asymptote, then how do we systematically find the m? Systematically, how do we find the m? Yeah. So, well, you can see from this, right, that this will be just like, so you can see equating the coefficient of t. What does that equating the coefficient of t? But yeah, this is the matter of you have to at some point take limits to be rigorous. Like you don't have to take limits to find the answer, but to be more rigorous, right? You should take limits. Well, the point here is that this M is this. Okay, so first thing is that there are no vertical asymptotes. Is that clear? Yeah, because if you tend to a point which is not infinite, if you tend to any A, you can see that X and Y both, tend to something. They don't, and they don't go to like Y. One second. The Y does not go to infinity, right? If when T goes to A, yeah, so here we are not going to say X goes to A, right? Because, so, well, the graph, whatever the graph is like this, but when T goes to a certain certain number, A, then the Y doesn't go to infinity. Yeah. So there's no vertical asymptote. Okay, so that's clear. Now the point is that if there is a slanting asymptote, so the M is, then how can we get this, right? So, well, you can then see that this is C by X. And so basically the M, what I'm trying to say is the M is equal to Y by X when maybe you can say X goes to infinity. Yeah, but you see X goes to infinity is the same thing as T going to infinity. You can check that it's just the same thing, right? That is the same thing as T going to infinity. Right? And this thing is equal to 1. Okay, so that's a little non-rigorous, a little bit, even what I've said so far. So let's see. No, so what we want to say, no, but this Y is not on the curve, right? This Y is not on this curve. Yeah, I mean that Y stands for the Y on the line. It's not understanding for the Y on the curve, right? So that's where we have to be a little careful. So how can we, but yeah, I mean, you can obviously put it and get the answer, but to say it more rigorously, we have to be a little more rigorous. Just a second, yeah. C is the asymptote. Yeah, so let me try to be a little more rigorous. So certainly from here you can get the answer, no doubt, but and also you can find the C in a similar way. But if you want to say this, then maybe we should okay, I can, there is a rigorous way, but yeah. So, well, what I'm thinking is we would like to show that we would like to say that this minus this goes to 0, right? Yeah. So we would like to say that T plus cos nt by T minus mx plus C goes to 0 as T goes. Yes, I mean that is right. And so yeah, in that case you can put that y equal to x of the asymptote and y equal to x of the line are the same. That is certainly correct. And if you use that what we did previously, then previously this y by x on the line, you can replace y by x on the curve. Yeah, you can put that and find the limit. That is fine. I don't have any problem with that. But I mean, that's not how we have defined, right? We have defined it as fx minus L goes to 0, something like that, right? So that's how we want to, let's try to see if we can do like that. So this thing goes to 0. And so from this basically implies that, let's see. So maybe by this we can find more, even this is not very rigorous. There is even a more rigorous way, but yeah, we want to see, this is slightly better, I guess. So remember the n here is fixed, obviously, it's constant, and minus C, and this thing goes to 0. Yeah. So then right? So, and this is when t goes to 0. So from here, just from this equation, can we find both m and c? Yes, t goes to infinity is what I meant. Sorry, Adish, what are you saying? Yes, because this is the asymptote, right? Because this thing, mx plus c is the asymptote, right? This is the y coordinate of the asymptote, and this is the y coordinate of the curve. So they must become closer and closer, right? The limit of their difference should go to 0, right? So this is sort of our definition of asymptote. Huh. Well, so you see, if you take any point on this curve, let's say you take a point P, right? Now, what is the y coordinate of P? Right? So this P is equal to, this P is corresponding to some value of T, right? And so this P will be T plus cos nt by T, right? And yeah, so this is the point T. And as the value of T becomes larger and larger, this y coordinate is the same as the y coordinate of the asymptote, whatever it is. Okay, and yeah, so their y coordinate should be. Yes, right. And so the y coordinates and x coordinates both will, the difference will be going to 0. I'm not considering, I'm saying y equal to mx plus c. This was initially a guess or an answer by some other means. Huh. Hmm. No, I'm not saying y coordinate minus x coordinate goes to 0. I'm saying y coordinate minus y coordinate goes to 0. Exactly. Yeah. When the x coordinate is the same for both. Yeah, right. Got it. Okay, good. So right, that is sort of what it. Yeah, and yeah, so from here, this is easy fact that you can figure out what m and c should be. That is okay. Yeah, okay. So again, this is not rigorous. This is not rigorous. One can point out flaws in this, but let's not go there. Okay, let's just keep it till here. Okay, and so from here you can find m and c, and you will get that m equal to 1 and c equal to 0. Okay, this is a simple question, but you can see that this is just knowing the definitions clearly. That's what we meant. We wanted to describe it, and because they've described it clearly, we kind of okay. Yeah. So the interpretation part is not so much yet here. We will see that yeah, there we will basically emphasize on infinity being special, and then we'll say it's not special. We'll see. Yeah, but let me just as a while we are at it, let me mention a more rigorous way. Sometimes you may need it. I'll not solve any problem using it, but the more rigorous way should be like this. So let's say that these are not graphs of functions, remember, okay? These are parameterized curves. Okay, so functions from R to R2, for example. Okay, so what you're looking at is, let's say, something like this. Okay, so if you are no, so right, yeah. So let's say that you're going to no, so this will just have a horizontal asymptote maybe. So this is not the graph of any function, at least not totally. So sorry, huh? I just said horizontal, but then I'm drawing something else. Yeah, so this is the point. Okay. So I mean, the better way to say it is that if this is the line, if this is the line y equal to mx plus c, okay, let's say this is the line L, and if the line L is asymptote to this curve, so this curve, let's say the point at this curve is, let me not say xt, it might be confusing. Let's say r1t comma r2t. So this is the general point, okay, on the curve. Then what we want to say is that the distance from this curve to the line goes to 0. That's what we want to say, right? The distance, so let's use this curve, right? C. Then we want to say that basically the distance from this curve to the line goes to 0. As t goes to some point, it could be a finite point also. I mean, it could be t equal to some a if there is a vertical asymptote, right? But otherwise, let's keep it like t infinity or minus, let's take t infinity, right? So this is really what the definition should be. Like the distance from the, like this at this t, I mean at this xt r1t comma r2t, the distance from here to this goes to 0. Okay, so, and that's not very difficult to find. There is a formula for that, right? I mean, so you know the formula. So if this is this is the line, then the distance from that point will be, so instead of y, you will put r2t, right? And you know the formula. So this will be like r2t minus m1 r1t, because what I did was what I did was not perpendicular distance, right? I was kind of doing something yeah, some it could be some other kinds of lines, yeah, because for the same value of t, you know, the curve and the line could be at different places, right? So that's not a very good way. It can actually give you the wrong answer if they're, yeah, if they are, yeah, they can get far. So anyways, the point is here that you get this and this minus c by, and then you know the formula, so you have to put some squares and square roots, and this yeah, that's it. This distance should go to 0. I mean, so if you take the limit, t goes to infinity, and this will rigorously, yeah. So, you know, wanting this limit to exist and being 0 will tell you the m and the c. Is it okay? You can see that this is really the more rigorous way to do it. Yeah, the distance. Okay. Okay. Right. Okay. Yeah. We said that. Yeah, but I did. Uh, but we kind of did a little bit of wrong thing there, because when I said y, when I wrote mx plus c, then this x, yeah, in this x I put this value, right? But how does that make sense? Not very much, right? So we are kind of using, yeah, it's okay, we are kind of using that, I mean, yeah. Right, but that is for a vertical line, yeah. If you take a non-vertical line, then yeah, there is a slight difference, right? So yeah, it will not, yeah, not always, that's the point. And yeah, okay, yeah, yes, that's fine. Yeah. So there was a slight, but let's not get too much into detail. I can say, but yeah, otherwise it will just get more and more confusing. So these are the two methods. Okay, broadly, all both are correct. Even the one mentioned right at the beginning about taking y by x and replacing y and x by the parameters that are given, that's also fine. Okay, that's also okay. So this is the thing. You see, this is a slightly interesting point. So yeah. Okay. So now as I said, yes, that is true. I mean, everything, yeah, all these are boiling down to something, right? Right. And for the thing for the curves, parameterized curves, they are obviously functions as graphs of functions are special cases of them. So that's also fine. Okay. I want to just, sorry, I got, oh, okay. Ah, okay, okay. So what is my voice not clear to other people also? What I said? Now it is clear. Okay, okay. So I didn't say that. So let's leave that. So let's move on. Yeah. So I want to just do an example. So an example of a maybe strange asymptote. So of a strange function with an asymptote. Strange function. This can be a maybe interesting example. Yep. So let me just write the question. Okay, let's just write the thing and try to do. So here you have this thing, fx equals to 1 by x plus sine 1 by x when no, so that's it. This is the definition. Yeah, when x is not equal to 0, it is not defined at x equal to 0, so it is fine. I mean, you can say that this function is from r minus 0 to r, right? Find the asymptotes. Oh, yes. Is it not showing up for others also? No. Okay. Okay, okay. So that's fine then. So let me then go to a different place. Otherwise, it will not work and we'll just end up wasting more time. So I'm just shifting. So give me a minute. Now everything will be fine. The space is also there because we're having some repair work going on. So I'll just, yeah, otherwise, no point. Nine. Okay. Now hopefully everything will be fine. Yeah, so am I there? Okay, now so the question already there. Okay, okay, just say find the asymptotes. Uh-huh. But there's no point in that because that's not a good sandwiching. There's a lot of space in between. Okay, yeah, it's between these two then. Okay, it's between those two functions. Okay, okay. Uh, okay. Okay, okay, right. That's all that is right. So then what then should be the x tends to infinity, x tends to, y tends to infinity. Yeah, y tends to infinity. Yes, exactly. So what Adish is saying is basically that's what it is. But the answer directly is just that sine 1 by x does not matter, right? And so you take the limit as x tends to 0, right? And so let's see, yeah, let's see. So if when x tends to 0, then what happens? Let's see. So if x tends to 0, we know that this is infinity. Okay, but then, yeah, how, why? No, no, see, that's fine. We can all see that. But the point is then, how does it follow from the definition that that is the asymptote? We want to conclude because we can all see that the y-axis is the asymptote. But how does it follow from the definition? Mm, that's mm, push towards x equal to 0. Hmm. Okay, that is not a good logic. I mean, you want something more rigorous, like so. If let us think. So, so I mean, the point is that see, all of us can see, right? All of us can see that the y-axis is an asymptote. But just from the definition, how would you get it? Like if this is the definition and this is what you have, how would you translate this to something like this? That's the only thing. X is yes, right. Then that translates. So that's my point. That what you just write is so y equal to mx plus c. If this is the thing, then in our case, what is happening is that this this is infinity, right? And well, I'm getting confused. 1 minute. So just a second. Yeah. So maybe so. I mean, this can also be taken as the definition of verticalism. Hmm. Hmm. I mean, because it is not going closer and closer to x equal to 0. Right. So that will be coming in the definition, right? Yeah. So not the slope, but both the slope and the exact thing has to come in. Yeah. No. So I understand your problem here, that you're saying that just this infinity means that there's a vertical line is shooting to infinity. Or which vertical line? Well, the vertical line is parameterized by the 0, right? The 0 tells you that it is x equal to 0, right? Yeah, but so, well, my point here is that limit no, but that limit is still infinity. That's not a problem. You can check that. That limit is infinity. You can check that. You should try to prove that. But, well, maybe we can say that this is the definition of vertical asymptote, right? Limit x tends to a, fx equals to 0 means that there is a vertical, or rather not e0 but infinity, meaning that there is a vertical asymptote. So the vertical asymptote definition can be this, and the other asymptote's definition was fine. Yeah, we can do that. Or I mean, this so if I have to just still do it, then this is, let's see, yeah, so this is 1 by 0 times x plus c. Yeah, that's what infinity is, right? I mean, that's the only way in which you can write infinity as a line, equation of a line. And then from here you can work out, right, that, well, so you know that it's a vertical line, and you can work out the c is 0. Right? I mean, maybe if that is any good. Nah, so 1 second. Yeah, maybe this vertical asymptote, we can just stick with this definition. That's not a problem. Okay, you can just take that. Okay. Otherwise, the c being 0, yeah, c, otherwise the c, we cannot really find the c otherwise. Again, we can still do it by a ratio definition and use 2 equations and so on, but you can just stick with this other definition for vertical asymptote, and then there is no problem. Okay, yeah, you can say in the paper, if you're writing, that my definition of vertical asymptote is this, and if they usually they'll just mention it also, but yeah. Okay, no, but that was not the point of this question, because so far there is nothing strange. Okay, so far we and everybody can say that the vertical asymptote is the y-axis. That's okay. Mm-hmm. Is this function Riemann integrable from 0, you are saying? No, this is not Riemann integrable, because the area becomes unbounded. In this case, you can try to work that out. Okay. For some, yeah, but that's why it's an interesting question. But for this one, it is not. This one, it's infinite. I mean, it's not a trivial fact. You have to work it. It's not hard, but you have to work it out. That it's the Riemann integral is okay. So your question is that if we take from, that's a 0 to 1 only, but after that it doesn't matter. After that it is simple. But if we take from 0 to 1, 1 by x sine 1 by x dx. Okay. So yeah, so the problem yeah, right. So continuity is not a problem. This function is continuous except at the endpoint, but non-continuity at the endpoint does not matter for Riemann integral. We have even seen that if it's discontinuous at infinitely many, let's say countably many, or let's just say at all integer points, and also it's Riemann integrable, because the places where it is not continuous, you can make the effect very, very small. We have discussed those things, but that's not the point. The point is that this function becomes unbounded, and not just the function becomes unbounded, but the integral is unbounded. Now, how you can do it? Just Like few classes back, I described the improper integral. So just use that. Right? You take t, find it at t, and let t go to 0. You see the limit is infinite. And that's your solid answer then. Okay. So because I mean, this is not a Riemann integral even. It's a limit of Riemann integrals. Okay. Yeah. Right. So from there you can say, and it's easy to see. I mean, 1 by x log t and so on. You can work that out. And so, but 1 by root x, then it will be, then it will work. Yeah, it will work. Okay, so 1 by root x will exist. 1 by x square will not exist. So yeah, we have seen these things. Yeah. Okay. So vertical asymptote was not the question. That was not the point. That is, you all can see that it has a vertical asymptote, but you can, we are learning to work out the definitions. But yeah, but the point is that when you see a vertical asymptote, yeah, then we all get this feeling that a certain thing that, let's say that this is the curve. Obviously, it is not like this. It is, so yeah, it is not like this, but I'm just drawing this and this is wrong, but it is wrong is what we're going to prove, kind of. This thing. But what you may think from this thing, and this can be a very good question, that when you look at this, then it may look like limit x goes to 0, f dashed x, or let's say x goes to positive 0, let's keep it even more simple, should be, any guesses? No, the derivative. So am I, no, not, yeah, so you mean to say tan of pi over 2, right? Infinity. Yeah, you just want a minus infinity or something like that, right? You just want to say that the function steeply, right, comes down. That's the meaning of a vertical asymptote, or it steeply goes up as you go to the left. So you would like, I mean, this is what at the first guess, if it was just the MCQ, and I mean, maybe you just say this, right? There's a vertical dot, 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 and what is the limit of the derivative? I mean, I maybe would have written this, right? But calculate it for this and see what you get. Okay. No, don't do it now. It's a simple thing, but do it as a homework. Find this. Okay. Or I'll just say, just ask, this is the wrong question in some sense, but the right question is this, what am I doing? Is this equal to minus infinite? Okay. Work it out. It's a good question. It's not hard, but just see. Okay. All right. That's why I asked this. And then you can try to explain, if it is not minus infinite, then you can try to explain. The answer will tell you, but then you can try to find an explanation as to why, how it could fail. Positive infinity. No, but it is decreasing, right? It cannot be positive infinity. Or, yeah, I mean, there's no chance it could be positive infinity. For x positive, for x negative, it will be, but maybe, yeah. Okay, so this is the interesting things. Like what? No, in fact, it will not be minus infinity. That's the, yeah, so you try to work it out, and then we can form the explanation. In a sense, yeah, try to work it out. So yeah, I just changed the place, so I had some things there which is not here anymore. So just give me a minute. What is the next thing I wanted to do? Yeah, so we should just do just some examples maybe to actually find out. Yeah, so let's just do an example to actually find out. Okay. Most of you will be good at this, but still let's just do it. Okay. Find maybe all asymptotes of, there is a function here, fx equals 2x square plus 3x plus 1 by x. Yeah. So try to find all the asymptotes. Yeah, vertical asymptotes are really a slightly different thing. Okay. Because of certain things. Yeah. All these exceptions can be taken care of once we build the right model, like that so-called projective space. But maybe we'll not be able to do that now. Okay, so oblique asymptote. Okay, now x equal to 0. Yeah, so you're saying, no, that's wrong. So that's not infinity. Oh, there's a 1 by x. Oh, sorry. Okay. So they're getting, okay. So first Adish has said a concrete answer first. So let's ask him. So why is x equal to 0 an asymptote? X tends to positive infinity. No. But then you're saying the asymptote is at, rather, then it's a vertical asymptote, right? Then x equal to 0 is not the, oh yeah, x equal to 0 is the y-axis, sorry. Yeah, right. Yeah, so that's what, yeah, that's right. So you take this limit, and this you will see is infinity, and so that implies y-axis x equal to 0 is an asymptote. Okay, so Sandan, is it clear? Because okay, so you are saying you have to compare the highest power of x and highest power of y. In what and what? Like, where is the y? But where is? So it is coming out to be equal, right? Yx is 2, but that's a strange method. That's not strange, but it's less straightforward. Yeah, so it's a book. Yeah. Uh, so you are saying you compare this, and so they are equal. Yeah, they are equal, and then then you put it equal to 0. No, but no, then I don't agree with the method. It's a strange method. I mean, so it may be, yeah, but try to follow the definitions and do this, because I don't understand that method is seemingly strange. Highest, because here it is 2, so I don't know what you're saying, right? I mean, I don't know. It's a very strange thing. Okay, so I mean, then that may, but try to just working out from the meaning of asymptote, like what we have learned today, the clear conceptual meaning Yeah, if we try to apply that, then do you see that y-axis, the y-axis is an asymptote, right? Because if you basically see at what point does the function shoot to infinity, right? First question is, at what finite point does the function shoot to infinity? Those will be vertical asymptotes, you agree? All of us agree? Yeah. At what finite points, at what finite a does the function shoot to infinity or minus infinity, right? And that a is certainly 0, because you can see, yeah, you can work it out. And so, Chandan, so is it clear that this y-axis will be an asymptote? Okay, because you see, I mean, if there is, so the curve may be anything, but if there is a vertical asymptote, it just means, and that's what I'm trying to say in today's class, that asymptotes are a very simple thing. It's just the limit, right? What does it mean? It means that the limit at x goes to a of the function is infinite. So finding horizontal asymptotes is simple. We don't need any method. Okay, like that. It's simple, right? So it is fine. And now, are there any other asymptotes? How do we find that? Are there any other asymptotes? Well, people can guess, I suppose, but we want to be able to say it clearly whether there are or there are not. By derivative? Okay. Okay, so you're saying that you take the limit. So this is the slope. So this is the slope at the point x of the function. So you're saying that you take the limit of the derivative as x goes to infinity, and this is 2, right? Is that what you're trying to say? And then so any line should be of the form y equal to 2x plus c. Any asymptote should be of the form y equal to 2x plus c. Yeah, is everybody following this? Yeah, the slope of the function and the slope of the line should be the same, and the only at infinity, and the only possibility, this may not work, but this is the only possibility that we have so far, that so far we've eliminated all possibilities. We are at 2, that it could be 2, and then so this is your thing, and then maybe you can so I mean in this case then y by x should be 2, but in this y by x is not 2, or no. So what am I saying? No, 1 minute. So it is 2, I suppose. No, so yeah, now you guys please work it out. I'm just waiting. I just wait. So let's all of you think and ask me if this is not clear so far. We do not need to do this, but we are doing this. Let's see. Yeah. This is the only possibility. There's no other possibility. 2x plus 3. All right. So when you have this, then you have something more to work with, right? So what you can then do is you can do 2x plus c, this limit. And now you see the good thing is, which I have said in the beginning of the class, is that you can take this, right? Once the point, any finite point doesn't work, then for any oblique asymptote, yeah, that closeness that you're trying to study, that can be studied when x goes to infinity. Y also goes to infinity maybe, or minus infinity, but it can be studied when x goes to infinity or minus infinity. Right? So that's the point. So you can figure out that this limit, sorry, you can enforce this limit to be 0, and then you can figure out that c is equal to whatever you can find. Okay, so you see, we actually do not need to do this, in the sense that just putting y equal to mx is just the easiest, it's an easy question. Yeah, it's the easy marks, in the sense that You just put this, and from here actually you can find out both m and c. You can see. If you work out, you will see. You can work out both m and c from the same limit problem. It's just simple. So just first find the vertical asymptotes and then go to the slant asymptotes. Obviously, this method has limitations. It's only working for graphs of functions, but it's fine. So to Rasubro, sorry. Yeah, and it's rigorous. I mean, there's nothing non-rigorous about this, right? It's also rigorous. Okay. So yeah, to Chandan and Rasubro, is this okay? This example. Okay, good. So I mean, what the method you have described, I can also talk about that a little bit later, maybe next time. But yeah, that is more useful when its equation is like, let's say, y square plus 3 or 3xy equal to this, some complicated thing. Then it's not the graph of a function. Then it's when the point we satisfy this implicity, then your method will be more better. But I'll talk about that maybe next time. Okay, I think we will have to do a maybe half an hour more later. So this thing, and yeah, so here from here, there are some things that one can say, that any rational function, so fx equal to, don't answer these questions now, just think about them. So if you have a rational function like this, then what can you say in general about as the asymptotes of it? Okay, for example, one question is that it has at most one horizontal, no, at most one non-vertical asymptote. It's a cool fact and easy to prove. It's an easy problem, easy exercise. Polynomial by polynomial, it will have at most one asymptote. Okay, I mean at most one non-vertical asymptote. Obviously, vertical asymptotes, it could have many. Yeah, you just take you can think, yeah, it can have many vertical asymptotes. Okay, so this is one thing that you can think about. So I did not do much today, but I suppose we did some easy stuff. Yeah. So next time I'll just spend some maybe 15-20 minutes discussing about the curves case. And as I said in the beginning of the class, try to put things on a more general footing and explain something. Okay. So then basically to the methods that Chandan was kind of saying, that method we can kind of prove. So it can become a problem that, if it comes in the exam, we can kind of solve it in a more, just that method of finding asymptotes, prove that that's the right method, kind of. Okay, we can explain. So maybe next class I'll do that for 20-25 minutes, and rest we can also work out finish the differential equation thing. So that can be one class. Okay. Parametric differentiation. Parametric, oh, you mean the substitutions, those kind of things? Can you say? Integrate that? What do you mean by integrate that? Good. That's interesting. Yeah, so I'll do that. And that kind of thing actually comes up sometimes, like solid volume of revolution. Yeah. Which are defined parametrically, but not as functions. Yeah, that is, yeah, okay. So we'll do that. Yeah. So yeah, I think this we can do in one class. So we'll not do differential equations, but that's also some problems we kind of opened up. But anyways, we'll do this and asymptote thing next time. That should be good. A little bit is left. The interesting thing is still left, but yeah. Okay. think it's fine. This stop here. It's already late for me. Gamma function is also there. It had come up sometime. I was